Hello everyone, it's a great pleasure to have here Caroline Huang today. Thanks a lot for accepting our invitation. Caroline is an NSF astronomer in astrophysics postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics. Previously, she was a graduate student at the Johns Hopkins University. She primarily works on studying evolved stars and their applications to distance and cosmological measurements. Today, she will present the Hubble Constant from Mira Variables. Caroline, please, you can start when you're.
Hi, everyone. Thank you so much for inviting me to give this talk. I'm very excited to talk to everybody here. So actually, the background of this slide I have right here shows Mira. It's that very bright red star above the word from. So I thought that was pretty interesting. So, oops. So even though everyone here is a cosmologist, I like to start with a little bit of history because I think it helps give us some perspective. So about 100 years ago, people were having a debate about how large the universe was. And one of the things they were debating were whether in these old astronomical images, these fuzzy blobs we saw were within our own galaxy, or they were equivalent to the size of our galaxy. And like which answer it was would change everything we know about the size of the universe. And the resolution for this eventually came in the form of Cepheid observations in the Andromeda galaxy. As most of you probably know, Henrietta Swan-Leavitt is the one that discovered that Cepheid variables could be standard candles. And this is what allowed Edwin Hubble to measure the distance to this galaxy and discover that it was much farther away than we originally thought, thus changing the size and scale of the universe. But not only would he use Cepheids to do that, he would also go on to create the first Hubble diagram. And that told us that as galaxies farther away were moving away from us faster, not only is the universe bigger than we thought, it was also expanding. So this told us that we don't live in a static universe. So this is just to illustrate how I think that studying the size and scale of galaxies nearby can be very illuminating for understanding our cosmological model. And now this tension that we are all aware of, the Hubble constant tension, is a tension between these indirect inferences of the Hubble constant from looking at early fluctuations in the CMB observations to the direct measurements of the velocities and distances of nearby galaxies using distance ladder methods, similar to what Hubble was doing. And so why do we usually have to make a distance ladder? Well, I really like this image that was made by Don Pesci, so I'm using it here. But there's only a few ways that we know of to measure distances, and distances are necessary in order to construct this Hubble diagram. But each method has its own limitations. So for example, we have radar, where you have known speed and a measured time, but it only gets you out to things within our solar system for the most part. Then you have parallax, where you have a known size and you're measuring an angle. And this gets us a bit farther to things within the Milky Way or kiloparsec scales. And then you have standard candles, which Henrietta Leavitt discovered the first version of in Cepheid variables. And with these, you can get to cosmological scales, so much larger than a megaparsec. And you also have standard rulers, for example, masers, where you have a known size and a measured angle. And these two also reach a cosmological scale. But because each of these have their own limitations, and only two of them on their own can reach cosmological scales, we generally have to put them together into a distance ladder in order to both get a calibration and a measurement that we can use for cosmology. So no one scale technique works for every scales. So one very common distance ladder that we build, we start off with parallax, and then we use parallax to measure the luminosity of some relatively more common primary standard candle, like a Cepheid. So for example, we'd look at parallax to get the distances to Cepheids in the Milky Way. And then from there, we would, knowing the luminosity of these Cepheids, use them to measure the distance to local type 1a supernova host galaxies, and by that I mean distances less than 40 megaparsec. And then from there, we would use these same type 1a supernovae, now with their luminosities calibrated, to measure the expansion rate directly in the Hubble flow at low redshift. So this is the Cepheid supernova distance ladder that the Rees et al. And Shu's team uses. And it's been very effective. So they've been able to achieve a precision of about 1% using this method, combining multiple anchors, many local hosts, and about more than 2,000 Cepheids. But if this method is so good, why would we want to look at alternatives? Well, now with this tension, we're seeing a difference that's greater than 5 sigma between the Planck measurements and the other early universe measurements, and then the late measurements of the Hubble constant. So because this could be an indicator of very significant parts of our physical model that we're missing, like we saw earlier with the doubling or increasing the size of the universe and the static to expanding universe, we really want to explore this possibility and make sure it's not as systematic, and to double check these Cepheid distances. So there's now been multiple different ways to measure the Hubble constant with this distance ladder method, primarily using Cepheids, TRGB, Miras, and now JWST, which I've forgotten to include on this plot. But with each of these methods, type 1a supernovae measure the Hubble flow directly, but we use geometric methods to calibrate the luminosities of a primary distance indicator, which then is used to calibrate the type 1a supernovae. So what I'll be focusing on today is how we use Miras to accomplish this goal. Okay, so one thing I like to think about is what makes for a good distance indicator. So there are lots of different ways to get distances, and I think people are coming up with new ones all the time. But the ones that get used the most typically have a combination of, I would say, these traits. So you want them to be high luminosity, meaning you can see them quite far away. You want the mechanism for why they should be a standardizable candle to be physically well understood. You also want it to have low intrinsic dispersion, meaning that you don't think that there's going to be huge variance in this class when you try to measure distance with them. You want them to be empirically calibrated, if not geometric. So either you can geometrically get the distance like you could with Cepheids, or you want them to be something that you can at least use a primary distance indicator to get the distance too. It's also good if they're relatively common, and related to that, if they're ubiquitous, meaning you can find them in all types of galaxies, and that they're easily identified. So I think in many ways, we have different distance indicators that don't have all of these traits, but we can build a distance ladder to expand our reach and compensate for some of these. And I think Cepheids are almost perfect distance indicators, except they're not ubiquitous. They are young, massive stars, so we can't expect to find them in all types of galaxies. So an illustration of this point, if you study stars, this image might give you a clue to that. So this is NGC 4258, and the Cepheid field, or this is the same field, but the Cepheid positions are shown on the left and the Mira positions are shown on the right. So with the Cepheids, you can see that they're definitely following some structure. They're more present in the dustier regions where young stars are being formed. Whereas for Miras, so these white boxes on here are the Mira fields. It's the WIF-C3 footprint from HST. And you can see that they're pretty much evenly scattered across this field, meaning that they're an older population. So this has also been true in our observations. We're able to see Miras in all types of galaxies and locations, but with Cepheids, we generally want to target like a galaxy that has star-forming regions. So most of these stellar distance indicators, like Cepheids and Miras, are variable stars. So addressing the second part, because of that, we do believe that there's a robust physical mechanism to assume that there are standardizable candles. So Cepheids are yellow supergiants that live on this instability strip, whereas Miras are thermally pulsating asymptotic giant branch stars. So you can see there's similar luminosity to Cepheids, but they're much redder than these yellow stars. And what a variable star is that it's actually experiencing changes in the brightness over time periodically. And this is, for these stars, they're due to these radial pulsations that are also fundamental, meaning the entire star is moving inward and outwards at the same time. And the pulsation amplitude is quite large. So what causes this pulsation? We understand that they're driven by changes in opacity, which occur in these partial ionization zones in the star. So these zones are layers where hydrogen and helium spent part of their time being ionized. So part of the time, the opacity will increase because the photons produced from reactions at the core go to ionizing these atoms instead of changing the temperature. And when they become unionized, these zones become more like free, they become less opaque, allowing the photons to go out. So because these atoms are at the correct temperature to be partially ionized, they spend part of their time being very opaque to radiation and part of the time being less opaque, which allows them to drive pulsations. And the locations of these zones within the star affect how large the pulsations are. So that's why there's this narrow range in temperature on the HR diagram that I showed, where the star is unstable to pulsation. Because if these zones are too close to the surface, there will not be enough material to drive a sizable pulsation. And similarly, if they're too deep within the star, you wouldn't see much of a pulsation either. We can also expect that within an instability strip, so for stars of a certain temperature, these pulsations should follow some kind of relation with respect to the size and mass of the star. So while modeling this is really complicated, the fact that a relation exists is pretty easy to understand intuitively. So let's picture that we have a star with some radius. We know that pulsational period is roughly just going to be the radius divided by the sound speed. And if we then assume a fixed temperature, like we have in the instability strip, which are these almost vertical regions on the HR diagram, then that means that luminosity is going to be proportional to radius squared for this star. So therefore, we expect that you're going to have a power law relationship between the pulsational period and the luminosity, which is exactly what we see. And that's why we're able to plot these two on a log-log diagram and find a line. Okay, so now that I've gone through all that, why would we want to use Miras? As I mentioned earlier, Cepheids are nearly perfect, but given the current tension, it is important to have independent methods for checking our systematics. So I think Miras are a particularly good alternative because they're highly luminous. As we saw, they're comparable to Cepheids on the HR diagram, and they're brighter than fundamental mode Cepheids in the near-infrared and infrared. So this is the near-infrared K-band period luminosity relations for Cepheid, fundamental and first overtone, and Miras for their two types, oxygen-rich and carbon-rich. So the oxygen-rich are in black and the carbon-rich are in gray. And this fundamental mode Cepheids are in red. So you can see that at the very longest periods, Miras are even brighter than Cepheids. And similarly to Cepheids, these stars follow a period luminosity relation, which we have a good physical motivation for. And they have low intrinsic dispersion. So you can see the scatter is quite low for these both of these groups. And we're able to empirically calibrate these stars in the LMC and NGC 4258. So Miras are one reason why they're ubiquitous, unlike Cepheids, which are yellow supergiants, is that their progenitors can range from about a solar mass to 8 solar masses. So this also has the bonus of increasing the size of the potential type 1a supernova local host calibrating sample. So the Cepheid distance ladder has already observed basically all the local type 1a supernova hosts that we can. And another bonus is that we'll be able to continue to do this research with the upcoming near-infrared and infrared facilities because Miras don't require optical observations for detection. So this is an example of a Mira light curve in the optical, but you can see how it has a very large amplitude of multiple magnitudes. So because of this, as you go into near infrared wavelengths, the amplitude decreases, but it's still large enough to be detected as variable. And okay, so now to compare these a little bit with some of the more commonly used other distance indicators, we can see that one part where they might be less advantageous is that you do need time series similar to Cepheids. But that's not true for some of the other distance indicators like tip of the red giant branch or JGB, which are done using only generally single epoch observations and a CMD. And it's also interesting to note that this JAGB method, which uses carbon-rich AGB stars, is also looking at asymptotic giant branch stars. So what is the relation between JGB and Miras? Well, both of these two methods are AGB stars. But the difference is that for JGB, instead of looking at the pulsational period or the pulsational mode of these stars, all of the carbon-rich AGB stars are considered as one population and identified using color cuts on a CMD. So for example, this is a plot from Sean's recent paper, but if you look at the LMC, on the left here, locations of the carbon-rich and oxygen-rich Miras are shown in red and green respectively. And you can see that this blue dashed line box is the location of the JGB. And carbon-rich Miras are one of the different AGB populations that make up the JAGB region. So there are basically all AGB stars pulsate, including those in the JGB by definition. It's just that they generally pulsate in different different modes. And since Miras are pulsating in a fundamental mode, you can see that they're just one of these different components of this region. You can see that these stars pulsate if you look at this plot from Abby's paper from 2024, where she showed that she was able to get a much more precise JGB measurement when taking average photometry over single epoch photometry. So I hope this helps clear up some of the differences between these two methods. But it's not all easy using Miras. There's a lot of downsides besides the fact that we need more data. And one of these is that it's still relatively new as a distance indicator, so we're still developing best practices. So as I mentioned earlier, Cepheids have been used for more than 100 years now, but Miras, their period luminosity relation wasn't discovered until the 80s. So it's much newer in comparison. They also have much longer periods. Their periods are 100 days or longer compared to the Cepheid periods, which generally cap out at around 100 days for the ultra long period Cepheids. And Miras are also astrophysically complex stars. They're not spherical, as we can see on the right, this is a deconvolved image of Mira that was taken using Hubble Space Telescope. And there's multiple spectral subtypes. There's the carbon-rich and oxygen-rich that I mentioned earlier. And our selection criteria, because we haven't used it as long, is less well-defined. So you can also see, this is showing the Mira period luminosity relation in a range of different wavelengths, where the oxygen-rich stars are in black and the carbon-rich stars are in red. You can see that at the shortest wavelengths here, which is I band, the period luminosity relation is almost flat. So this is partially why it took them so long to be discovered as standard candles, because you really need to have near infrared data to see these linear relationships between luminosity and period. The other thing I'll note here is that this diagram is made using mostly single epoch observations. So if you had multiple epochs, you would see much lower scatter. So this is just to give a sense of how the period luminosity relation changes across the wavelength ranges that we can observe. So as I've mentioned a few times, Miras can be oxygen or carbon rich, and this is based off of the photospheric C to O ratio. So the short period stars tend to mostly be oxygen rich. And the reason for that is the way that carbon rich stars in general, AGB stars, are formed. So these stars generally start on the asymptotic giant branch as oxygen rich. And if they can dredge up enough carbon from the center of the star, then they will become carbon rich. So this is also why the mass and the ratio of carbon to oxygen rich stars in an environment depends on the initial metallicity as far as we're aware. So this is one more reason why we might not want to use carbon rich AGB stars in our period luminosity relation, besides the fact that they show much larger scatter here. So the carbon-rich Miras are also more heavily affected by molecular absorption, which is the main cause of the scatter that we see on their peel at shorter wavelengths. Okay, so as I've alluded to, we prefer the near-infrared and infrared for these stars for several reasons. So they're cool stars, first of all. They're only about 3,000 Kelvin, so their spectral intensity peaks between 1 to 2 microns. We're less sensitive to extinction than in the optical. We have smaller amplitudes, smaller cycle-to-cycle variations, and we can use colors to separate the two types potentially with the near-infrared. But we also need to have time series observations, and they generally have to span a year, and we want about 10 epochs that cover multiple phases. And this is for distances. If we just want to identify where they are on the CMD, we don't need as much information. So with all that said, the current Mira distance ladder is HST based for consistency, and it consists of two anchors, 4258 and the LMC. 4258 is a host galaxy to a water megamaser, which has been used to get a geometric distance, and the LMC distance comes from observations of detached eclipsing binary stars. And then we have two type 1a supernova host galaxies. This number is small and could be much larger with more observations. So right now we only have NGC 1559 and M101. And putting all this together and using the Hubble flow sample from Reset All 2022, we get of type 1a supernovae, we get an H0 measurement of about 72.37. So there's a lot of areas here where it might be clear for improvement. One of those is maybe getting another anchor. So one of the things you might be wondering is why we haven't gotten a Milky Way anchor. And part of that is because of what I've mentioned earlier. Parallax is actually very difficult to get precise distances with for AGB stars, because AGB stars are extended and complex objects. So this is an image reconstruction of an S-type AGB star. So Pi Gruis from Pioneer and VLTI. And so the top and bottom are just like different models of the same observation, but you can see that there's a lot of structure in this star. And if you wanted to identify the photocenter, that's actually pretty tricky. So another thing that we can see is that the size of the star is very large. So because parallax and angular size both scale as 1 over distance, and the radii of these stars are larger than 1 AU, the angular sizes are always going to be larger than their parallaxes, which makes like determining the photocenter of this star very important for getting precise parallax measurements. And with these convective cells, that changes where the photocenter is. This isn't the only reason why it's difficult to measure parallaxes for AGB stars, but it is a main contributor as far as we understand. There are ways to get around this, but that's why we haven't used any Milky Way calibrations of these stars yet. Okay, so the next thing is moving on to how we actually use these, how we actually look for Miras in the hosts of type 1a supernovae that are nearby is first, after we've collected our time series observations, we generally want to start by looking for objects that are quite likely to be variable. So we calculate a Stetson variability index. So this might take something like 100,000 stars in our region, our observational footprint, to 3,000. And this is mostly just to weed out non-variable stars, not really to select this is not really as a classification. And then with our starting set, we'll just fit all the periods of these stars and apply our selection criteria, which we've developed from looking at NGC 4258, 1559, and M101. So this generally takes our sample of 3,000 stars down to a couple hundred. And then we figure out which sample is actually robust for Hubble constant measurements by calculating the crowding limits, the completeness limits, and doing some cross checks. So what I've shown here at the bottom is just the different selection criteria we used in each of these galaxies that we've observed with HST so far. And so I'll just highlight a few of the different steps that we take. And one of them is the completeness limit and the carbon-rich exclusion. So one of the main things that we try to do is to remove carbon-rich contamination, because as you saw earlier, it causes the PL relations to have larger scatter, and they also at longer wavelengths follow different PL relation as the short period oxygen-rich stars. So the way we do this is we calculate the 0 point as a function, the 0 point of the PL relation as a function of period. And we expect two trends. Basically, we expect that at shorter periods, the 0 point is going to be biased bright because we're reaching the completeness limit. So stars that are, the PL relation has some width due to the width of the instability strip, and stars that are fainter than the PL relation are going to be not detected, and stars above will be detected, which will cause a brighter 0 point at shorter periods. And similarly, at longer periods, we expect that since there will be more contamination from these carbon-rich stars, that we're going to see a fainter 0 point. So as we look at how the 0 point changes as a function of period, we can identify where we see these trends and remove those areas. So that, plus the amplitude cuts that we also apply, removes the vast majority of carbon-rich stars. But we know that we won't be able to remove them all with only two filters. So basically one color, and just our sparse time series data. So for the remaining contamination, we calculate how much we expect that it affects the 0 point by modeling the contamination using these well-studied samples in M33 and the LMC, to model the effect of increasing the carbon to oxygen ratio, the carbon star to oxygen star ratio as a function of period, and what effect that would have on 0 point. So we're able to model approximately how much the 0 point would change in the galaxies that we observe. So this is an example of what we did in NGC 1559. In M101, when we did this, we actually found that we expected no carbon-rich contamination. And in NGC 1559, we found a few hundredths of a magnitude of an effect on the 0 point. Okay, so for M101, which is the more recent type 1a supernova host that we've looked at, we ended up with, after all of these tests, a sample of about 200 Miras with periods from between 240 to 400 days. But our total original sample before our cuts was about 288 days when we were including objects with periods of up to 500 days. And you can see, here's the footprint from Hubble. We had a ton of different observations when we included the archival ones. from previous observations that were aimed to study the light curve of the supernova, which was actually in this field. You can see the locations of the Miras in blue, and they're pretty evenly scattered across this region, which is always a good sign. And our study had an observational baseline of about 2,900 days, and we incorporated the previous observations in gray that were originally intended to study supernovae. So you can see that when we combine these longer baseline but more sparse observations with our more recent in blue observations that were spaced more closely in time, this really helped us nail down the periods, and that the periods appeared quite consistent over the course of our observations. So another thing is, if we look at these Miras in the optical, so this is not from M101, but this is just an example of optical and near-infrared light curves from the LMC that were observed by Ogle. You can see that in the optical, the light curve does not look that sinusoidal, and it also has very large variations, for example, in I, but at the top. But then if you go to J, H, and K, we expect much smaller amplitude variations, and they're also more regular. So while we didn't have any very well sampled observations for one specific star in M101, we were able to create this plot here on the right, where we put together all the observations from all the stars, only correcting for mean magnitude, not for amplitude or anything else, and plotting it as a function of phase. We could see that we basically get back a very sinusoidal looking composite light curve, which is encouraging because this suggests that they are really one pretty standardized set of objects. So the major sources of uncertainty that we still have actually come from the number of type 1a supernova hosts. We're really limited by the fact that we've only measured Mira distances to 2 type 1a supernova hosts. But this is because each type 1a supernova has an intrinsic scatter of more than a tenth of a magnitude. So with 2, we can only get down to 1 over square 0.1 over square root of 2, essentially. And all the other uncertainties that I've talked about are actually subdominant to that at the moment. But even without having an extremely precise Hubble constant measurement at the moment, we can still compare distances to these 2 type 1a supernova hosts that we have observed. And that lets us check for systematics that could have arisen in the first 2 rungs of the ladder. It also sidesteps potential differences in the supernova hosts, or in the type 1a supernova catalogs used in the Hubble flow. So if we cross-check rungs 1 and 2, for example, with M101, we can see that the Miras are within 1 sigma of both the Cepheid and TRGB measurements to this galaxy. So the Mira PL relation is shown in the left here. And on the right, we have all the literature measurements of Cepheid and TRGB to this galaxy. And the Mira measurement is in black at the bottom. So the gray shaded region shows the 1 sigma uncertainties from the Mira observations. The blue dashed line is the mean of the measurements from Cepheid and TRGB in the most recent 15 years, I think. And then the black is everything. As you can see at the beginning, there was a lot more variance and some bias towards this larger distance. So if you exclude that, it gets even closer to the Mira measurement. So this is pretty reassuring. And now what we're doing is observing these fields with JWST as well. So I had a cycle 2 program where it was a joint HST JWST program that was recently completed. The HST part was recently completed. The 3 HST epochs are used for getting the phase of the single JWST observation we got of M101. So the Mira field is this red footprint you see here, where this is a Cepheid field. One of the Cepheid fields in this galaxy is this green region. And the JWST observations are these blue, NIRCam observations are these blue footprints here. So this will allow us to image both the Cepheid and Mira fields. And for the Mira part, with all these filters that we've gotten, 6 near-cam filters, we will be able to test our selection criteria because we now have more colors and we can create color diagrams. So we can test our HST-based selection criteria and potentially correct for color excess that could be due to mass loss around these Miras. And we can calibrate the PL relation in new filters and mitigate crowding. So mitigating crowding is a pretty straightforward one, which people have talked about before. But this is like a false color image from HST on the left and from NearCam on the right. And we only had 2 filters with HST, so I reused F110 for 2 of the colors. But you can see how much less crowded these same Miras, which are in red, are in NearCam compared to how they were in WFC3 IR. And this was also something that Adam had shown with Cepheids was the case, and Cepheids were part of our program as well. And for Miras, when we create these closer in views of the field. And so the other thing that we saw when we got JWST observations with Cepheids is that this didn't change the measurement of the distances, but it did decrease the scatter a lot. So that was a good sign that the crowding corrections were doing the correct thing. But that we could improve the precision of these individual PL relations with JWST. So we're now working on doing this with Miras as well. Hopefully that paper will come out relatively soon. And another thing we found is that if we compare both the Cepheid Mira and also TRGB and JGB measurements with HST and JWST, they're all pretty consistent, which is encouraging. So the HST Miras are in green, and they actually are a little more offset than all the other measurements right now due to the fact that we have fewer supernova hosts, so we have larger variance there, but they're all consistent to within 1 sigma, which is very encouraging as well. And specifically for the Miras, we'll also be doing these cross checks I mentioned where we can compare model color diagrams of AGB stars with our observations and hopefully check the classification. And finally, before closing, I just wanted to add that I think Miras are very interesting for other reasons, not just for cosmology, although I get that that's what this group is most interested in. But they're very astrophysically interesting stars because they have high mass loss rates. So this mass loss has the potential to enrich the ISM even at early times. So if you see Martha Boyer's work, that's discussed a lot in there. Recently, they've also been used to map out the structure within the Milky Way. So that's what's shown in the upper right here from Iwanek et al. They have individual precisions of about 6.6%, which allows them to do that. And also, the pulsational physics of stars is very sensitive to their internal structure for the reasons I discussed earlier. So it does give us some ability to provide feedback for models. And recently, one way that this has become apparent is that nonlinear pulsational models are necessary in order to reproduce the fundamental mode period luminosity relations, which I'm showing here. And finally, there's also a lot of interest in maybe looking at long period Miras, although they're more difficult to separate from carbon-rich stars and follow a different PL relation, most likely. But they're extremely bright. As we saw earlier, they can be much brighter than Cepheids. So the longest period objects might be detectable to redshift 0.08, which would mean that you could bypass the supernova part altogether. But this is obviously not something that we know how to do at the moment. It's just potentially possible. So I'd like to leave with my summary slide, just saying that I think independent cross checks of our distance measuring methods is really important, not just to compare Hubble constant results, but also to compare distances to intermediate galaxies. I think Miras are especially exciting because they use infrared and near infrared observations. And this has been a big focus of astronomy now. This method is still pretty young, so there's a lot of avenues for improvement. Right now, the most precise measurement of the Hubble constant is about 4%. in total uncertainty, which is not very small, but it does confirm the higher local H naught with about 95% confidence. And these stars also have a lot of applications outside of cosmology as well. And with Rubin, we'll be able to just detect them in galaxies that are up to about 10 megaparsecs. So if you can think of other ways to use these stars, that would be great. So that's all I had today. Thanks so much for having me.
Thank you so much. Thank you. Very nice talk. Any questions? Adam?
Hi, Caroline. Very nice talk. So do you have any early indication of how your photometry between JWST and HST compares?
Yeah, actually, I found that the JWST, and so I haven't redone the JWST photometry after they put out the new Dolpha release, which I've heard that we should do. So with that caveat, they seem to agree quite well. There's only one thing that we're working on at the, or I'm working on at the moment, which is that sometimes I think the wrong source is being identified in James Webb for a subset of those stars, which we can identify with the HST observations. So I think right now it's more of a matching issue than like the photometry not agreeing. So either the JWST magnitude is pretty much exactly where we predict it will be, or it can sometimes be very off, which indicates that I think I'm accidentally selecting the wrong JWST source. So I'm working on that at the moment.
And I assume you're using some kind of color correction because the filters are a little different.
The filters are a little different. Yeah. And
Yeah.
I just at the moment I'm just doing like a very at the moment I just empirically calculated a color correction using like statistically what the offset seems to be, but I would like to go back and get the correct color correction after we figured out the matching issue.
Thank you. Sayantan?
Yeah, thank you, ma'am. Very nice talk, actually. So I am actually from relativity background, like cosmology. So could you like go to the slide, like where you give the relationship between the speed of sound and the luminosity and the standard candle thing? I mean the Mira.
Yeah. You mean the hand wavy explanation?
Yeah, roughly.
Yeah.
Yeah. So I'm just asking that it follows from like the hydrodynamic equilibrium, not like some relativistic Tolman-Oppenheimer-Volkoff, right? It's a completely non-relativistic calculation in a sense that. So the details of the calculations. These stars are probably very non-relativistic, right? I mean, these calculations has been derived not from say Tolman-Oppenheimer-Volkoff, right? I mean, rather from the just Eddington relations.
Yeah.
Yeah, so and I am asking that could you tell about the Vs? Like, I mean, is it just the Vs squared is just, I mean, dp by d rho itself? I mean, because p and rho drastically change from center to radius. I mean, I know this is a very naive question, but I was just wondering that, I mean, yeah.
I don't think that's naive. I think so. This is a very rough explanation for the PL relation. So it's true that the sound speed is going to change a lot internally. Here we're just assuming some mean sound speed. And so I was mostly just trying to get at assuming a fixed temperature like we have in the instability strip. We know that the pulsational period is mostly going to depend on the radius of the star, but you can't actually use this to derive like what X would be. That's not something that we can do very well. So that's why we try to actually calibrate what this X is empirically, because you're right, there is mean sound speed is not really a good approximation for getting any sort of theoretically calibrated period luminosity relation. So I don't think that's silly at all. This is just to give some kind of like physical intuition for the problem.
Oh, okay. Yeah, actually, that's what I got confused because R is constant. The Vs changes drastically. So the pulsation would also change yeah. So, okay, now I understand that it's a rough intuition you are trying to give, like, I mean, how the scaling works.
Because the actually trying to do this is very complicated.
And why it has to be say power law? I mean, like, I mean, is it could be like say with some logarithmic correction, etc. Like, is it like there is a say Eddington relation, like there is a empirical scaling law, or is it just something you assume? Like, is it how much assumption is there and how much a numerical thing has gone through? Like, could you just comment on why it is power law is expected? Like, I mean, could it be say logarithmic, or I mean, is it like some kind of like Eddington scaling relation, etc.? So that's what I was wondering.
I'm not entirely sure what you mean actually, but the way I'm trying to convey it here is that luminosity is proportional to radius squared, right?
Okay.
Yeah, so now we have a relationship between luminosity and period, and they both are a function of radius. So we don't know exactly what that, like what radius, you know, how it comes in to this, like we don't know what the x is, like the power law relationship between the two of them, but we do know that both of these could be described primarily as a function of radius, if you believe me about using mean sound speed. If you don't, then we have issues there, but that's the only thing I'm trying to say here.
Thank you, ma'am.
No worries.
Thank you. We have a question in the chat. The question is, do we know the general requirements for ground-based telescopes to observe them? Assume near-infrared observation is must, but are there other requirements as well?
This is more of a question of where you would want to observe them, I think. So we've seen Miras with a bunch of different near-infrared telescopes, like the Hubble survey has detected them in the optical as well. TUMAS has observed Miras, assassin surveys. I mean, it's more the fact that it's difficult to get, if you're asking about whether we can use them to measure more type 1a supernova host distances, the reason why that's difficult is because now we have a different photometric system from the rest of the HST based distance ladder, and the resolution of these space-based telescopes is much better. So I think those are, we worry more about crowding, I guess. And I don't know what other requirements you might be intended by this question. Primarily, we haven't used the ground-based to maintain a consistent photometric system, and because we're looking at galaxies where resolution might be an issue. So as I mentioned for Rubin, we'll be able to see these stars out to about 10 megaparsecs. The thing about Rubin is that even the longest wavelength that Rubin will observe is not a great wavelength for Miras, so to speak. Like, it's not near infrared. So you do really want some near infrared or infrared observations to put them on a PL relation. If you only have the optical observations, the PL relations can be very flat, like what we saw here, like in the I band. And actually, if you go to shorter wavelengths than this, like the V band, they might even be negative, as in, or not negative, but like the slope will be negative on this diagram. Like, you'll see that the brighter stars are actually the shorter period ones. So it's just difficult to use these stars in the optical. So I think that's why for Rubin, it'll be great for getting periods out to 10 megaparsecs and probably some PL relations too at the shorter wavelengths, but it might not allow us to automatically improve the Hubble constant.
Thank you so much.
Okay, thank you.